Okay, hello. So welcome to this new room here. I'd like to talk about E8 and the octonions. So part of the moral of the story, by the way, is this. So I started out talking about Young diagrams, which are a great tool for understanding classical groups. Classical groups, to some extent, are groups of symmetries of the most simple mathematical objects that the mathematicians like to study, like vector spaces, or a vector space with an inner product, or a finite set. And so we can develop the theory of those classical groups and their representations, and it turns out that they're remarkably unified by Young diagrams. But then I turned to Dynkin diagrams, and that really exemplifies a somewhat different philosophy to life. Namely, one way to think about them is that you could get interested in Lie groups, groups that are also manifolds, basically because you like the idea of symmetry, as exemplified by group theory, and you also like the ability to use calculus or differentiation, which means you should be working with manifolds. So a group that's a manifold is a perfect combination of symmetry and the techniques of calculus. And then you discover that while Lie groups are wonderful, there are just too many of them to completely classify them. So you limit yourself a little bit, or a lot actually, by focusing on compact Lie groups. So compactness, this marvelous topological property, changes the story a lot. And I showed you how we can basically, I didn't tell you all the details, but it's true that you can completely classify compact simple Lie groups. They have an abelian part that's just a torus. And then this other part, this semi-simple part, which is much more interesting and complicated, but we can still classify compact semi-simple Lie groups, so we can classify them basically by Young diagrams, although the same group can have various covering spaces that are also groups. So there's a little bit more information than just the Young diagram. And the advantage of this other philosophy is that it turns out that it leads us into thinking about things that we never knew we were interested in. Whereas in classical groups, we sort of already were interested in vector spaces and sets before we started studying representations of classical groups. So it turns out that when we study the compact semi-simple Lie groups, we discover that they include things that we might already have been interested in, like rotations in Rn, and then slight generalizations, like basically rotations in Cn, namely the group Sun, and then generalizations that we really might not have been knowledgeable about, like rotations in Hn, the quaternion analog of those other two groups. But then even stranger groups that we had really had no idea about, that nobody had any idea about before they started classifying the compact semi-simple Lie groups. And those exceptional Lie groups, as I explained last time, all are connected to the octonions. And so we're thrust into some mysterious world that we had not deliberately entered just by our attempt to try to understand a combination of symmetry, calculus, and compactness to keep things sort of tame. And so I want to have a little bit of fun exploring this strange new world. So I want to tell you a little bit about E8 and the octonions. And so I started telling you about it last time, but I suddenly, at the very end, discovered a mistake I had made, which is very good. It's very good that it was at the very end, because then I could just say, well, okay, I'm done, and then fix it now. So remember what I've been doing. I've been trying to describe to you the E8 lattice, the E8 root lattice. And to get it, a good way to think about it is you start with this one thing I can call the checkerboard lattice, which is the Dn root lattice. And so that's the lattice that you get if you have an n-dimensional checkerboard of alternating white and black, red and black hypercubes. And you just put a dot in the middle of each black one in this kind of checkerboard, higher dimensional checkerboard pattern. So more mathematically speaking, what we're doing here is we're taking n tuples in Rn that have integer coordinates, but not all of them, which would be like using all the squares in the checkerboard, but just every other one, namely those such that the sum of the coordinates is an even number. So that means that next to any one of those squares that is occupied, you have a square that's, you have squares or hypercubes that are not occupied because the sum of the coordinates is odd. So what we get is a picture like this. I'm going to draw it in 2 dimensions, even though that really doesn't capture the beauty of it. But I just want to do a low dimensional example. So here we have the origin, and then we have the points 1, 1, and the points 2, 0, and the point 1, -1, and so on. And so this is supposed to be a kind of diamond-shaped pattern. In this particular case, it's really just a square lattice that's been rotated 45 degrees, right? A square and a diamond are just the same shape seen from 2 different angles. So you may just think this is like a fancy way to draw a square lattice, but that's just in 2 dimensions, that the checkerboard lattice is itself a square lattice. Of course, I could have drawn it so terribly that it doesn't even look like a square lattice, but this is a square here. That's what I mean. And I can't write lots of fancy numbers and talk at the same time. Is that right? Something like that is right. So every other dot, is it still screwed up? No. That's a negative. Yeah. So you start with those points. Okay, you can do that in any dimension. And then what we do is we double the density. That is, we put in a whole bunch more points. And last time the mistake I made was to think that you would put these new points that I'm about to draw in the sort of obvious places, which are the places that are as far away as possible from the existing ones. That's what I drew last time. But in fact, that turns out not to be the thing that we are going to do. What we're going to do is then double the density of points in this way. So we'll form this new thing which people call dn plus. And what it is it's the union of 2 copies of dn. So one of them is just our friend dn here, and the other is a translated version of dn, where we take the points in dn and we add the number 1/2 to all of their coordinates. So we can write this as dn plus the vector 1/2, 1/2, 1/2, and so on. So that's just a shorthand for take every point in here, add this vector to it, and get a new point. So that's 2 shifted copies of the dn lattice. But notice my picture last time was screwed up because these new points we're drawing are not like here and here. They're in this sort of stupid locations here, like this, where I add 1/2 to their coordinates. So they're not as far away as possible from the existing points. So it may seem like a sort of weird thing to do. But it turns out that when n is equal to 8, so when you're in 8 dimensions, the new points have distance at no less than the square root of 2 from the origin. I'll show you why in a second, but what's the point about the square root of 2? Well, that's just the distance. That's just the distance of the closest old point. So the distance between this and this point here that was already in the dn lattice, that's already square root of 2. That's the closest points to the origin in the dn lattice are distance square root of 2 away from it, because the closest you can get is have 2 1s and the rest of them be 0s. So which is also the shortest, which is also the norm of the smallest vectors in Dn. In other words, those also, they're closest. Also, the vectors in Dn have points at least square root of 2 away from the origin, except for the origin itself, of course. So why is that true? Well, you just calculate it. So the closest new points to the origin will be the ones where you can check, will be the ones where you just take the origin and then you just add this vector to it. So you'll get a vector that's just a list of the halves, n of them, or more precisely 8 of them. And then if you take the length of that, sorry, I really can't talk about it anymore at the same time. If you take the length of that, so you get 1/4 plus 1/4 plus 1/4, all square rooted, and you have n of them. So you get the square root of n over 4, or in other words, the square root of, well, let's leave it like that. And so when n equals 8, this is the square root of 2. So even though we've put these new orange points in a sort of funny location, just shifting them over by adding this vector with all 1/2, when you get up to 8 dimensions, they're just as far away from the black points as the black points are away from the other black points. Here I focused on the origin, but of course the whole lattice is translation invariant. So what I'm telling you really is that the new points have distance square root of 2 away from anything in the original lattice, just like the old points in Dn were that far away. So we've doubled the density while not making any points be closer to each other than they had been before. Yep.
I'm confused. So that orange point that's in the middle of the black line, the coordinates at that point are 1/2, right?
Yeah.
Right. So
this is not dimension 8. This is dimension 2.
Oh, right,
so we get square root of 1/2.
Gotcha. Yeah.
So So here so that's why this seems stupid, right? I mean, yeah. So this is, it's good that you said that, Tom. So this is like square root of 1/2. It's obviously closer than this guy here. Okay, but when we get into 8 dimensions, it doesn't work like that anymore. The new orange ones are the same distance from the origin as the closest of the old black ones. Okay, so that's weird, but that's how it always works. In high dimensions, there gets to be lots more room, and so you can stick things in between other things in ways that your low dimensional intuition does not make evident. So this lattice that we get in 8 dimensions, this Dn plus lattice in 8 dimensions, that's the E8 lattice. That's called the E8 lattice. So we define the E8 lattice, the E8 root lattice, that way. So E8 is DE8 plus. So let's just get to know it a little bit. So first of all, one nice thing that I won't prove, but it's pretty easy to prove, is that there's another way to think about it. You can think of E8 as the lattice consisting of these 8 tuples of real numbers, which have these properties. Either all the coordinates are integers. So of course that's what we had in the Dn case, or they're all integers plus 1/2. And of course that would be true of these shifted points. And the sum of all these coordinates is really can't find, is even. So it's easy to check that the sum of the coordinates, if a guy in Dn is even, then it's easy to check that for these shifted guys, the sum is even, because if you add up all those numbers, you get an even number. But it's not instantly obvious that while these statements are true about the D8 plus lattice, they in fact exactly characterize the points in the D8 plus lattice. But it's pretty easy to check that these points are all of this form. It's just you just fiddle around with them. Check it. So that's another characterization that's sort of nice and very widely discussed in the literature. So I could have just told you, here's E8, but I think it's a lot more fun to think about it in this way that I've told you, where you start out with a checkerboard lattice. It's not a very exotic concept, and then you notice that in 8 dimensions, there's a magic way to double its density while not putting points any closer to each other. It's some beginning of a sense that like 8 is special. Dimension 8 is special. So let's count how many points in the E8 lattice are closest to the origin. They will actually be the roots of the E8 lattice. So this is the root lattice. And there are these roots or root vectors in the E8 lattice. And remember, from the general theory, the idea is that reflecting along those vectors gives you symmetries of your root lattice. That's what it means to be a root vector. You can reflect along it and it maps the lattice to itself, and that those reflections generate the whole symmetry group of the lattice. So the root vectors in the E8 lattice happen to be the shortest non-zero vectors. That's how it works for a bunch of, but not all of the different diagrams. And so, but what I want to show to you is that there are 240 of them. So let's just count them. So first we can look at the ones. First we can look at the ones that were already in D8. So the shortest vector, the shortest non-zero vectors in D8 well, I already told you they're going to have length square root of 2. Well, I didn't tell you, but I alluded to it. So what are all of those? So you get them like this. You can do like plus or minus 1, 0, 0, and then this is, we're in 8 dimensions, so I get a total of 8 coordinates here. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So that's 1, right? That's a vector that has length square root of 2, and it's in the D8 lattice. But of course, there's nothing special about putting them in the first 2 coordinates. We could have put these 2 guys in any of the coordinates. So we could permute the entries in any way we want, and we get a whole bunch. And that's all. Those are all the ones that have length square root of 2. Because the next kind of vectors are the ones that have like a 2 in it, and those are already longer. So how many are there? Well, there are 4 choices of these plus or minus 1s here, and then we're picking 2 out of 8 entries to be non-zero, so we get 8 choose 2 choices of which 2 entries we make to be the non-zero ones. So we just have, that's how many there are. 4 times 8 choose 2. So let's just figure out what that is. So it's 4 times 8 times 7 over 2 times 1. In other words, it's 4 times 56 over 2, or in other words, it's 4 times 28. And since I've done this calculation a lot of times, so I know what 4 times 25 is, right? So it's going to be 112. So there are 112 of those guys. But then there are going to be a bunch more, which are coming from these new vectors we've thrown in, these orange guys that have these 1/2s. So how many shortest vectors, i.e. vectors of norm square root of 2, are going to be of that sort. Can somebody tell me? Can someone tell me anything about how you start figuring that out? You don't have to count them and just instantly tell me, oh, it's a really easy calculation, but you could just tell me something.
I think you can argue that every component has to be plus or minus a half, and then you just count how many possibilities there are.
That's basically right. Yeah. So there's a little extra little twist, but that's the basic idea. Yeah. I mean, the ones that are in this translated copy, they all have to have entries that are integers plus a half, and as soon as you get up to 3 halves, that's too long. So that's definitely the right track. So the shortest non-zero vectors in this D8 plus translated by this vector. Well, so as he said, they've got to be of this form, plus or minus a half, plus or minus a half, and so on. Anything else would be longer. These ones we already saw have length square root of 2. So that's good, they're the same length. So they also have length square root of 2. But what's the slight catch to counting these? Well, how many are there of these? 2 to the 8th, yeah. But the problem is that the guys in the E8 lattice, it has to be that when you add these all up, it's an even number. You may remember, right? So that's not true of all of these. We could get these, we could pick these so that they add up to an odd number as well. So there are 2 to the 8th of these, but only half of them have coordinates summing to an even number. I mean, I'll just let you think about that a little bit. You just play around with some and you'll see that. I mean, obviously, if you switch one of these signs, it's going to switch from adding up to an even number to switching to an odd number. So that's why half of them are going to be even and half are going to be odd. But you just have to make sure, just make sure that you, well, that basically proves it. In fact, you just have to check that there are some that add up to an even number and some that have an odd number. But if they're all pluses, they'd add up to 4, and if you flipped one of those to a minus, then it would add up to 3, and so on. So yeah, it's pretty simple. So we just get 2 to the 7th, which is 128. Yeah, they're only in the E8 lattice. So that's it. So they're 112 in our original lattice and 128 in our translated lattice, and then you just need to know how to add. And so it's 240. Yes. So there are 240 of these points in this beautifully symmetrical arrangement, it turns out, although you can't it's beautifully symmetrical. But that's a good way to think about what's going on. So there's a theorem that's extremely hard to prove. Says that in 8 dimensions, if I take a ball and I start trying to get as many other balls as possible to touch it, but of course the balls can't interpenetrate each other. So I have a ball radius 1 and I try to have as many balls of radius 1 touch it. The maximum number is 240.
John, you might want to write slightly bigger on this grayish board.
Okay. Yeah, thanks. Yeah, I knew that this fading magic marker problem would occur too, which is also part of the suspense of the whole thing. So in dimension 8, well, this is called the kissing problem. You didn't know that balls are extremely romantic in 8 dimensions, but you can kiss at most 240 balls of the same radius. And so if you think about what we've just done, by centering balls at the E8 lattice, we've seen that you can get at least 240 to all kiss the central ball at the origin. But of course, the hard part is really that you can't do any better than that. But we proved the easy part. Okay, so from this, we can do some other cute things. So one thing is that this is really irritating. It's not like anybody who has a magic marker secretly tucked away in their backpack. Like when I teach at UC Riverside, there are like students who are well organized. You just like go, here, I'll save you. I see one here.
I'll go get some more.
Okay. Okay. If you're willing to let me use this precious resource, thank you very much. Thanks.
I'll go get some more anyway.
Okay. Okay. So we get a lot of other funds from this stuff. So one thing is that what we've seen is that the D8 lattice, the D8 root lattice is included in the E8 root lattice, right? But it turns out, well, I've sketched out very sketchily that these root lattices give rise to compact Lie algebras and compact Lie groups. So in fact, that process of getting the Lie group from the root lattice is functorial. It's functorial with respect to inclusions. So it induces a Lie group homomorphism. So in other words, there's a Lie group corresponding to D8. Well, let me say start out with the Lie algebra homomorphism. You get that first. Dn is the root lattice of the Lie algebra SO2n. So the Lie algebra SO16 of rotations in 16 dimensions is the one that corresponds to D8. And that actually gets included into the Lie algebra E8, the Lie algebra of this Lie group E8. And then I said that, well, I said it in a nice fancy way that the category of Lie algebras is equivalent to the category of Lie groups that are connected and simply connected. So that if you have a map of Lie algebras, you get a map of the Lie groups. So we get a Lie group homomorphism from this Lie algebra homomorphism. So the most obvious Lie group whose Lie algebra is SO16 is called SO16 in big capital letters. That's the rotation group in 16 dimensions. But that one's not simply connected. That has its fundamental group in Z mod 2. So we have to take its double cover to get a simply connected one. And this has a name, by the way, for those of you who are into this stuff. That's called the spin group. But I just mean that, don't worry about that if you don't know what that means. It's just the double cover of the group. And so that's simply connected. And so we get an inclusion of that into the sorry, but this may not be an inclusion, but it's definitely a homomorphism. That's all I want to promise you. Into the Lie group E8. So this construction that we've done actually shows you that there's this large rotation group or double cover sitting inside E8. What can we do with that stuff? Well, one thing we can do is we can form the quotient space. So we can take the quotient of E8 by the image of this. And I'm sorry, I forget if the image of this is SO16 or spin 16. That is this group, this map may be like 2 to 1 or something. And not quite sure, but I'll just act like a mathematician here and say the image of I. So this will be you can take a quotient of a Lie group by a Lie subgroup, and you get a manifold, and it's a manifold on which it's a homogeneous space. That is, it's a manifold on which this group on top here acts. So the manifold on which E8 acts, that's just because when you do a quotient group, the elements in there are these little cosets, for example, right cosets, and then you can act on this collection of right cosets by left multiplication, perhaps a coset to another coset. So we get this interesting manifold with the group E8 as symmetries. So what is this manifold? So, well, if we know a little bit of stuff, we could work out the dimension of this manifold at least. And I think I'll just sort of tell you the result. Its dimension happens to be 240 minus 112, or in other words, 128, for reasons that are very closely connected to this calculation here. But a little extra work required to work this out. This guy here actually has dimension 240 plus 8. And this guy here actually has dimension 112 plus 8. But when you do this quotient space, you subtract those two numbers, and that's the same as this, so it's 128. Now, what's so great about 128? Well, it's a power of 2, of course. That's what's basically it's great about it. But it's also the dimension of the octonions, tensor the octonions squared. So the octonions tensor the octonions in some algebra that I mentioned a while back called the octooctonions. It's a non-associative algebra. And it has dimension 8 times 8. So that's dimension 64, but its square has dimension 128. So the O tensor O squared is what you would call the octooctonionic plane. If you could imagine doing the plane in this weird number system where the coordinates in your plane were octooctonions. So this manifold has the same dimension as the octooctonionic plane. And I told you about something. I told you about some mysterious thing called the octooctonionic projective plane, which is the octooctonionic plane with some points at infinity tacked on. And that is, in fact, this manifold. So, in fact, E8 mod MI is what I was talking about. I called it O tensor O P2. And I told you there's this 128 dimensional manifold, which has a Riemannian metric on it, whose isometry group is exactly E8. And that's this guy here. So I've shown you there's this manifold of the right dimension. I've sketched. And I've shown you that E8 acts on it because it's a quotient of a group by another group. So that's all you need for that. And what about this Riemannian metric stuff? Well, if you have any Riemannian metric on a manifold, and you have a compact group acting on that manifold, then you can average with respect to the action, average by doing integration with respect to the so-called Haar measure on your compact group. You can average it out, and you can get an invariant metric. So whenever you have a compact group acting on a manifold, it will have an invariant Riemannian metric. So this has an E8 invariant Riemannian metric. And that's the one I was talking about before. And in fact, it has just one up to rescaling, up to multiplying by a number, and such that E8 is the isometry. So that's a harder thing to show. That's much harder to show. If there's no other transformations that preserve this metric besides the ones that we have made preserve the metric. So that's how you get the octooctonionic projective plane. And so I told you that what we would love to do, some of us, would be to think about the octooctonions, figure out projective, some mutant version of projective geometry with octooctonions, define the octooctonionic projective plane, and then define E8 to be the isometry group of that. That would be like a geometrical explanation of E8. But in fact, that's not where we're at. Nobody knows how to do that. All we know how to do is to build the group E8, then take a quotient of it by something and get this space. So
I haven't heard about that from my week.
yeah.
So what I know, vector spaces by taking spheres and then dividing out by opposite sides. So what goes wrong with that here?
Well, RPN, the real projective spaces, are just, RPN is just a n sphere with antipodal points identified. When you get to CPN for the complex projective space, then it's not that. You can think of it this way: you take the unit sphere in CN, and then you identify all points that are you can get from one to the other by multiplying by a scalar, by a unit complex number. So you're not just identifying opposite points, you're identifying all points along a circle that's multiplied, where you take a point and multiply by e to the I theta. And then for the quaternions, it's like goes on, you have to do even more modding out. In all those cases, the thing you're modding out by is like the unit real numbers, the unit complex numbers, that is the ones with norm one, the unit quaternions. Those are all groups because those division algebras are associative, but the unit octonions, while they're closed under multiplication, are not a group. So what do you mean by modding out by a thing that's not a group? That's an example of the type of problem that shows up. And for O tensor O, it's even worse because O tensor O is not even a division. It's not even a norm division algebra. So the unit sphere in O tensor O is not closed under multiplication at all. So it's just worse. So you're sort of leading me on to where I want to go, which is what is the octonions exactly? So for starters, let me clarify here. So when I say a normed division algebra, what I mean is a finite dimensional real vector space. Every vector space in this class is finite dimensional. A with a kind of multiplication. So it's just some bilinear map, say multiplication going from A times A to A. We want it to have a unit. We want there to be a unit element. So we want an element 1 in A such that 1 times anything is that thing. When you multiply on left to right. And I don't want to impose the associative law. I don't want to make this be an algebra in the usual associative algebra sense. But I want to make it be normed. And so we want to have a norm. I'm going to write the norm as like an absolute value. So that's just the usual concept of norm, which assigns to any element some length is from 0 to infinity. But then the key property is that you want the norm of a product to equal the product of the norms. And so that property there kills off most examples and leaves a very select few examples of norm division algebras. And the marvelous theorem due to Hurwitz is that there are just 4 of isomorphism. So every norm division algebra.
We haven't talked about the division part of the definition.
Well, yeah. So this sort of gives it to you. So what obviously this shows you is that if you multiply by anything non-zero, that will have a trivial kernel. You can't. So there's no zero divisors. It actually takes more work to show that any element actually has a multiplicative inverse. In the associative case, the difference between having the step from going from having no zero divisors to having multiplicative inverses is not so hard. From the non-associative case, which from my point of view is like the only interesting case in this definition, it's a lot harder. But it turns out that this actually implies that every element has both a left and right, has a thing that's a left and right inverse. But that's not trivial.
Do you need to say something about the norm of 0? Otherwise, your norm will be 0 everywhere.
Oh, well, a norm is never. No,
oh, we see a norm in the usual sense.
Yeah, right. Yeah. So a norm is like,
yeah.
The only things that have norm 0 are 0.
Yeah, right.
The norm obeys the triangle inequality. The norm of a constant times something is the constant times the norm. If that constant's like a positive real number, all that junk. The usual norm stuff. Yeah.
Right. I didn't know which we are throwing away associativity. I didn't know which other.
Yeah.
So throwing away. Right.
Yeah, that's right. No, it's just associativity that we're throwing away. So this would be like a. Yep. So every norm division algebra is isomorphic to one of 4: the real numbers, the complex numbers, the quaternions, and the octonions. And this one here, this last one, is non-associative. So basically, everyone's reaction to this should be like, yay, yay. So that's sort of the sequence, the gang of 4 algebras, sequence of decreasing enthusiasm on the part of most mathematicians. But then, of course, people who like this stuff, they go, whoa, that's like something new and interesting, really new and interesting. So I want next time to actually define the octonions. There's a very nice way to construct the octonions. And I won't give you the whole proof that it's a norm division algebra, but I'll just show you how you prove it. But what I want to do in my remaining time is to show you that these octonions are really necessary for understanding the exceptional Lie groups. So here there's like some vague clue that's going on, that the E8 is the symmetry group of this manifold whose dimension is just the dimension of O tensor O squared. But if you're a skeptic, and you probably should be, this is sort of fake here because I just defined this thing to be O tensor OP2. I did not construct it using the octonions. So you might think it's just some kind of coincidence. But there's another connection between E8 and the octonions, which shows you from like a completely different angle that there's something going on here that's not just a coincidence. So the normed division algebras, all 4 of them. It's very funny to be proving general theorems, by the way, about norm division algebras. Sometimes it's good to do, but you're just really covering 4 examples, which is sort of weird if you're used to like studying groups or something like that. So the norm division algebras have lattices in them that are closed under Well, of course, every lattice is closed under addition and subtraction. It's a discrete subgroup, so I don't even need to write that. But the interesting thing is also under multiplication. So they're sort of like sub rings of the division algebra, but I can't really say ring in the non-associative case. These rings are associated. And here's how they go. So some of them I've already talked about, actually. So R has, of course, in it the integers. That's the lattice that's a subring. That's the unique lattice that's a subring of the integers. And this is you can also think of this as the A1 lattice, the lattice for the Dynkin diagram A1. And I should say, maybe you want to say up to rescaling or rotation, but it's. And that remark will apply for all of these cases and be more interesting in the other cases. For the complex numbers, I mentioned that there are two. They're the Gaussian integers, where you throw in I, so you get the square lattice that's closed under multiplication. And so I mentioned that that's isomorphic to the lattice A1 times A1. That's just a way of saying it. This guy in here is given by a pair of integers, and it's geometrically just the product of two copies of the integers, as a with its distance function as well. But then also, you could take the square root of negative. You can take a cube root of 1 and throw that in there. And so you get what are called the Eisenstein integers. That's just the name for it. And I pointed out that's isomorphic to the A2 lattice. The quaternions I mentioned have this thing called the Hurwitz integers, which are the quaternions A plus BI plus CJ plus DK, where either all of these guys are integers or they're all half integers. So either they're all in the integers or all half integers. That is all integers plus a half. So these guys are closed under multiplication, and they're called what are they called? The somebody else integers. I'm blanking out on this guy's name. Is it Hurwitz? Yeah, it is Hurwitz. Okay, yeah, Hurwitz. I was just thinking it's sort of weird because Hurwitz should be like the non-associated guy. But yeah, these are the Hurwitz integers. That's what they're called. And that's isomorphic to the F4 lattice, which, by the way, is isomorphic, which is to the D4 lattice. That's slightly less exotic. Exotic lattice. I always get confused about these things, but I think that's true. I think they're on screw up in certain ways here. Okay, but the cool part is that it even works for the octonions. So the octonions have something in it called the Cayley integers that's closed under all these operations. And it's isomorphic to this E8 lattice that I was talking about. So you can think of the E8 lattice as integers in the octonions, in the sense that you can add them, multiply them, subtract them, stay in there. Here, the way that this isomorphism is actually just a little bit tricky. It's actually a little bit sneaky to describe how you do it. And in fact, the first person who, one of the first people who discovered this actually got it wrong, and John Conway mocked them for it, named something name them the Kermsey integers because they're wrong. They're not closed under these operations. And when I was starting to think about this, I made the exact same guess Kermsey did. It's like an obvious guess for what it should be, which is wrong. So I'm going to stop here. And so next time what I want to do, just to let you know, is I want to tell you what are the octonions? Like how do you actually multiply octonions? And yeah.
So for R, you mentioned E was the unique one, right?
Yep.
So it's probably, I'm just messing up my definition. Why does something like E going square root 2 not count?
You're right. It does count. So what I really, to kill them off, what I want is I was trying to say that these are basically like a subring. And I said that they're closed under multiplication, but I forgot to say the other thing. They contain one. They contain the identity. So now say what you were saying again.
If you
for the
like,
R?
For R, if you say something like Z, but like some stuff like A plus B square root 2.
I didn't even need to admit this mistake here. Okay, so no, that's not a lattice, right? So that's dense. The things of the form A plus B squared root of 2, or A and B in integers, that's dense that's a dense abelian subgroup. So a lattice is defined to be for starters, a discrete abelian subgroup, and then we want it to make it not be too small. We say it has rank equal to the dimension of your vector space. So if you say all that junk and you say it contains one, then we're forced into the integers. If I hadn't said it contains one, you could have said the even numbers, right? The even numbers are closed under all these operations, but they don't have a unit. So
and in that case, in that case, is it easy to see why it's unique, or is it like a big example?
I think it is easy to see that it's unique. Any lattice will have, well, it depends what you mean by easy, but any lattice has a point in it that's the closest possible to the origin. Otherwise, it would be a dense subgroup. So take that one, negate it if necessary to make it be a positive number. So there's got to be some smallest positive number in here. If it were any smaller than one, all its powers would give you even smaller numbers. So it can't be smaller than one. So it has to be bigger than or equal to one. So it can be like 2, but that would violate this. So if you demand that it contains 1, then it just has to be 1. Yeah.
A couple of questions from Zoom. Will we hear about the Freudenthal magic square?
Maybe. So I'll say this. So I was telling you about how we get exceptional Lie groups as symmetries of these funny things like projective spaces, like O tensor O P2 or O tensor C P2 and so on. It turns out you can take any two norm division algebras and tensor them and form a thing that's like a projective plane. So you could do like H tensor H P2. And so you get a square of possibilities, and they each have a symmetry group that's an interesting Lie group. And you get all the, you can get all the examples that I talked about and more. Yeah. But I don't know how much I want to go into it, but it's fun, definitely fun.
Okay. And then, so this question was asked 13 minutes ago, which is maybe when you're about on Hurwitz's theorem.
Okay.
Is this related to the Moufang projective plane coordinatized by the octonions, a classical example of a non-Desarguian plane, Desarguian implying associativity of the coordinate ring?
Yeah, it is definitely connected in certain ways. So of all these weirdo projective planes, the least weird of the weirdos is OP2. That actually is an honest projective plane in the sense that it has points, lines, any 2 points that are different lie on a unique line, and any 2 distinct lines intersect a unique point. And this can be constructed in ways sort of like you were describing, namely like taking O cubed, taking the unit sphere and then modding out by some stuff. And so that very heavily relies on the fact that O is a norm division algebra. And by the way, the non-associativity of O is what prevents you from marching ahead and defining something like OP cubed. There is no OP cubed Because when you're dealing with that many numbers, the non-associativity kills you in certain calculations. It's very hard to prove that there's no OP cubed because you'd have to define exactly what you mean, what you want from it. I guess it's not that hard, but it takes work. You have to say what you want it to be before you can prove that it doesn't exist. And typically, no one has been that systematic about it. So people typically, new people keep coming and saying like, I found OP cubed, I made it. And then you have to sort of beat them into submission by saying like, well, you found something, but it sucks. It's not good. So it'd be better to prove a theorem about what you want OP cubed to be before, so that you can prove that it doesn't exist. But basically, the consensus of experts is that there's no such thing, and so the buck stops here at OP2 for these constructions. Yeah. Yes.
So that isomorphism at the bottom is that an isomorphism of non-associative ring? Is that what you're saying?
Well, this has a non-associative ring structure.
Yeah.
Because it's contained, by definition, these are like things.
Sorry.
And E8 starts out life as just a lattice. And so what I'm going to do here is this lattice here, its shortest vectors, the way I cooked it up, have length square root of 2. Yeah. So I got to shrink them down so they have length 1. Yeah. And then I have to pick some isomorphism between that R8, that Euclidean R8 and O. Right. Euclidean vector spaces.
Because there is a different way of constructing that, which I learned from John Conway.
Constructing what?
Constructing E8, right? What
the lattice?
Yeah, you start with the quaternions, and inside of it, you've got the binary Coxeter.
Yes.
And you look at the Z span for that, which turns out to be 3 being equivalent to like 8, which means it's not discrete, right?
Yes, the golden ratio is shown up all the time.
Jiggle the, that's right, it's root 5. You can jiggle the inner product. You get an inner product on that ring.
Yes.
And that turns out to be E8.
Right.
But of course, it's not the same multiplications.
Oh.
Because that one's non-associative.
Oh, right.
So that's kind of weird. I mean, I've never realized that I could think of it in that way rather than the Conway construction. Yeah,
that Conway construction is very beautiful, and depending on people's tolerance for this sort of weird exotic stuff, there's like a lecture I could give about that kind of thing that I happen to love, which is that you can start with the dodecahedron or icosahedron, and from that you can get both this exceptional Dynkin diagram called H4, which is one of these weirdos. H4. This one here. And that's the symmetry group of a beautiful solid in 4 dimensions called the 120 cell. But then moving on but then you can also think of that solid as a subgroup of the unit quaternions, and it's this subgroup you're talking about. And then from that you can build up E8. So so there's this weird connection between leading you from the icosahedron up to E8, which is very beautiful.
I mean, the other thing you can do with the ring construction of E8 is you can construct with each lattice as a modulus very easily.
Very easy. You can think of the Leech lattice, which is a 24-dimensional lattice, as sitting inside a product of 3 copies of the E8 lattice. Yeah. So Greg Egan and I mean, other people have done it too, but Greg Egan and I spent a bunch of time working out stuff about that. Yeah.
And there's one more question from Zoom, and then maybe better wrap up. Are these the only lattices in RC, H, and O? Don't we also have D8 in O?
Yeah, no, there are other, of course, there are tons of other lattices, but the more exciting question would be like lattices that are closed under all these operations. And already there are more that I didn't mention. So like a sort of semi-boring one is that there's another one that, like, for example, the Gaussian integers were sort of boring because they're just sort of like integer coordinate points. There's a thing like that you can do with quaternions. Just quaternions with integer coordinates is a lattice that's closed under multiplication. And then I haven't told you what the 7 dwarves are that are like I, J, and K that are the things for the octonions. But if you know what those are and how to multiply them, then you can just take integer linear combinations of 1 and those 7 dwarves, and you get a lattice It's just like an 8-dimensional version of this thing. It's sort of boring integral lattice, but so what I've focused on here are like the less obvious ones. And if you're into this stuff, or wanting to get into this stuff, there's this book by Conway and Smith called On Quaternions and Octonions, and they consider all these different kind of forms of integer forms of the quaternions and octonions and systematically study them. So that's where I stole a lot of my knowledge.
Okay, thanks. Okay, guess we leave it there.
Okay, thanks a lot. Yep, great.